In this example, I want to find all points of inflection and intervals of concavity. Now, when looking at my function here, it begins by x to the 1/2 power. So I do have a domain restriction. X to the 1/2 power I know is the same thing as the square root of x. So I do know 0 is included, but I know I cannot have a value of x that is less than 0. So my domain, I just want to keep in mind, I can have x values that are greater than or equal to 0. Okay, so we know to find inflection points where concavity changes is by taking the second derivative and setting it equal to 0. We then must also verify that there is a change in concavity at those values. So first derivative, required to use the product rule. So derivative of x to the 1/2, x to the negative 1/2, times the second part, plus x to the 1/2 times the derivative of the second part, which is just 1. Anytime I need to take the second derivative, I do want to simplify as much as possible. So here we have x plus 3 over 2 square root of x plus the square root of x. Again, to simplify more, I'm going to get a common denominator. So over here we need a 2 over square root of x, 2 square root of x. And that part in green there is simply the number 1, so we do not adjust or alter the function. So now we have x plus 3 plus square root of x times square root of x is just x, and we have a 2 all over that common denominator. Let's get crazy here and combine some like terms. So we have 3x plus 3 all over 2 radical x. First derivative. But again, I'm looking for inflection points, concavity, so we're talking second derivative. Second derivative will be required to use quotient rule, low times the derivative of the high, minus high times the derivative of the low. All over the low squared, which in this case will be 4x. Again, let's simplify. So we have 6 radical x minus 3x plus 3 over the square root of x, which is all over 4x. I'll get a common denominator in the numerator. So here, I know I need a square root of x, square root of x. Now I have 6x minus 3x minus 3. Don't forget about distributing that negative sign through. And we have square root of x, and then that's all over 4x. Using the definition division here, I'm going to multiply both top and bottom by 1 over 4x, or the reciprocal of 4x. So we'll get our second derivative in simplified form to be 3x minus 3 divided by 4x to the 3/2. So to find inflection points, we're going to set this thing equal to 0. The 4x to 3/2 is where the second derivative would be undefined, but that is at 0, and 0 is already an endpoint. So we'll set the numerator equal to 0, add 3, find an inflection point to be at 1, possibly an inflection point. So next we'll create our number line. This is, again, it's just to help me stay organized. I know I have to start at 0. The function is not defined for anything less than 0 and 1. We're going to plug test points into my second derivative to determine concavity. Okay. So I see my first derivative there. Let's plug in a number larger than 1. So if x is 2, in the numerator, plugging in 2, we have 6 minus 3, positive. Plugging in 2 to the bottom, also positive. So I know I'm concave up from 1 to infinity. And next, let's look at a half. If we plug in a half, well, we know the denominator will be positive, but if we plug a half into the numerator, we get a negative value, so we must be concave down. Now, with this change in concavity, we can conclude then that we do have an inflection point at x equals 1.